welcome everybody to this research seminar. We are celebrating this year, at least starting from 31st of January, the 60th anniversary of the Institute. And we are planning to have a series of research lectures. And the first one is by Kurt Schmidheiny. He's a professor at the University of Basel. And he studied in Bern, and he had his PhD from the University of Bern. And since then, he traveled all over the world, in particular to Barcelona, where he spent 5 years, I think. And he publishes a lot, in particular in the areas of taxation, location, wealth distribution, and he uses individual administrative data a lot. And this is, of course, of interest to IHS, where we plan to use this data also. And we have already used such data in the past. And I hope we will hear an interesting talk, which sounds very technical. But as I was told, it is extremely important in application, and everybody who wants to do event study has to know this paper, which has a lot of citations already, I have heard. And so the floor is yours, and please let us know what this is about.
Thank you very much for the nice introduction. I didn't say it's super important, I said it's very trivial. But I actually also think it's useful. Then it's for you to judge whether it's also important. Yes, so it's a great pleasure to be here at the IHS in Vienna. First, it's a great pleasure to be at the IHS because I've heard a lot about this institution, starting with Andreas Reichtcan, who was my professor in sociology, who taught me all about how to work with data. And he was a postdoc here, and he taught me a lot about the institute. And then there was Klaus, who was my PhD supervisor, and also talked, of course, a lot about the IHS. But it was a place that he actually took, so it's the first time here, and it's great to see that it really exists. Then second, it's also nice to be in Vienna. I'm Swiss, and Vienna is really Weltstadt, and it's something that we do not have. Although we have now the same population as Austria. When I was a kid, Austria was always bigger. This is going to change. Maybe this or next year we're going to overtake you in population. And still, I think our largest city starts where you second city, which you don't even consider a real city like this. So Vienna is different. It's wonderful. It's great to be here. So event studies. What is this about? It's all about this type of graphs that you have seen in lots of empirical research, I guess. Recently. So this is the kind of graph that we see a lot now in public economics, labor economics. Almost every empirical paper will have that kind of graph. So what is this? It's a graph that we call an event study graph. So this is a paper from Sebastian Siegel, who is the co-author of this paper, published in 2018 in the AR. We were together doing a sabbatical in Berkeley a year and met there, and he was right then publishing the paper. So what do we see here? This is about the German Gewerbesteuer, which has different tax levels in different municipalities in Germany. And it looks like when a municipality increases the Gewerbesteuer, when this has an impact on local wages. And what you see here, the line here, that would be large increases. So there were municipalities that increased their local Gewerbesteuer by a lot. Then we would have a decrease in the real wages in these municipalities. And what this graph shows you, and why it's so useful, is it shows you the dynamics. It shows you, okay, when there was a tax increase immediately, and this is the 0.0, there was a reaction there, not yet statistically significant, but then it increases to grow, and actually after 4 years, it seems to flatten out and is a large significant effect. The second thing that this graph provides, it also gives you estimates from before. Now, why would we think about an effect before? We don't think it's an effect, but we want to test whether this is kind of a comparison of a treated group, which is like the outcomes here, compared to a control group, which would be the 0 line. And what we see here is the pre-trends. So we are now at the same time estimating whether these groups were differently already before. And that's kind of it's not a real formal test, but it's a suggestive test whether there are parallel trends, which is the main assumption for these effects to be causal effects. So the identifying assumption you need is these two groups, treated and control group, have the same effects after the treatments. So now at least we can say they had the same development before. We see it in the same graphs, nothing significant, and then it starts. So that's the kind of evidence that people want to see. Shows you the dynamics, shows you the pre-trends. Now, what you also see here is they do that exercise for only large tax increases, which are significant effects. Then they do it for all the increases, which are kind of the right direction, but nothing significant. They also do it for decreases, and then the pattern is kind of not very compelling. Now, this is not totally satisfying because you would say, well, taxes, tax rates, this is not like a 0-1 treatment. You get the drug or you don't get the drug. It's something continuous. So taxes go up a little bit, a lot, they go down. And when you define the treatment as large tax increases, you have a very weird control group. These are all the places that have small increases or no change or decreases. That's a completely heterogeneous group, which is not a good control group. So in principle, I mean, in econometrics, we want to use the information about the quantitative size of the treatment. So what they suggested to do is to actually multiply this treatment dummy variable with the magnitude of the effect. And they did the exercise, plotted the graphs, and then the editor of the AR at the time told them, you're not allowed to do that. That's a regression of levels on changes, and that's totally weird and cannot be meaningful. So you're not supposed to do that. They still wanted to use that information. So they said, let's use something very old-fashioned, which is something time series distributed lag model. Just regress changes today on changes with lags. Now, a year before, period before, 2 period, 3 or 3 periods before, and you get estimates for that. And then you can accumulate up these estimates, and you should get something very similar in spirit, like the event study. So this is what they did on the right, which is an estimated distributed lag model with cumulative effects. Now, is that, well, how can we get these pre-trends into the picture? I mean, distributed lags are usually lags. So this is what you see here. Starts with time -1, then at the point of impact, then it goes up. So then they included leads rather than just the lags as well, and cumulated up as well. Then they just start here at the starting point. This is not totally comparison because now you said, well, that in principle now at -1 you already have an effect, it's not significant, but why not actually put that down here? But distributed lag, this is just a method on its own, you cannot just do whatever you want. So they included the starting point. So then we started discussing that as in principle, these two things I think should be the same, and you should just move this graph down here. And I think we have to understand that. And I needed to understand because at the same time I was working on this paper, which was on wealth tax rate in Switzerland. It's now published last fall in the AHA policy. So here the story is similar. We have different wealth tax rates in Switzerland. So it's a tax on wealth, which is quite unique. And it's the tax that is discussed in the US, or was at the time, from Elizabeth Warren, and we were the first to actually provide empirical evidence on that. So we had already a paper when I went to Berkeley, which was using fixed effects or panel data, and we had very strong effects, very large effects, and people very much criticized our results by it's kind of a traditional econometrics of fixed effects, diff in diff, I don't know, that's not very convincing. And all the seminars in Berkeley would have these graphs and say, well, I can do that too, I mean, but I really need to understand what's going on. So that's the result from doing an event study with my wealth tax rate. And again, we started using event study. We needed a 0-1 treatment. So we just said, look, there are thousands of different tax rate changes. We just take the largest one and we call them an event. A large tax decrease, a large tax cut. What was the effect? And here we look at the tax base. So how does wealth, reported wealth, react to that? And what you see now, if cantons in Switzerland make a wealth tax cut, a large one, then immediately wealth goes up, reported wealth, and it goes up quite dramatically by here in these estimates between 20 and 30%.
Okay, can I so the wealth tax increases, and what do I see here? So I see
increase. I mean, here is log points in the reported aggregate wealth, the tax base. So this is a semi-elasticity here. And we see the effect, which is very large. Now, the paper is about what could these channels be. We figured out there is in-move, there is wealth, people with wealth moving into these places after they announce the tax cut, but it's also that individuals who are already there seem to report more. Could also be, in principle, that they save more, they invest more, but we have not seen any of these. This is now using individual level administrative data. We do aggregate it, but we do have the full data, so we can look at all these channels. So we don't see an effect. Savings, we don't see an effect on investment and so on. What we see seems to be declarations. They declare more money. They might have hidden some money before. And people are moving in, rich people from other places and from abroad. Okay, this is not the paper, but to understand the story. But it's the same kind of graph. So you see here, there's an immediate impact that goes on and seems to flatten out at some point. But actually, these cantons with the tax increases, they were not really statistically different in their development evolution before. So that's very nice to have it in one graph. But again, it's not very compelling to actually think of a large tax cut compared to all the other things which could have been tax cuts, but smaller ones increased. So,
I mean, you can easily just compare it to the zero tax cuts, right?
Yeah, but there might be very few of them, right? I mean, this is kind of a continuum. There are always little changes. Okay. In particular, we look at the effective tax rates. So actually, and that would also know, it could be a trick, but then you're losing a lot of information. And in principle, I mean, I'm educated in traditional econometrics. I do actually think that quantitative information has some value. If there is something large happening, there should be, if there is a large treatment, there should be more effect. And I want to. So we also did that and estimated a distributed lag model, which is now much even more convincing in the result. We're using this quantitative information, but different from Sebastian. We were now willing to actually put zero, because in the meantime we really understood what's going on here. What's the link between a distributed lag model and an event study? And that's the whole point of this paper, is to show this is actually just. I've just heard that in Austria we would say ident. So it's the same. It's just the reparametrization of the same thing. And once you understand that, you can easily turn the 0-1 dummy variable into something continuous. It's traditional econometrics. The whole thing here is as old-fashioned as a different or at least that's what. There's nothing new to it, but people very much like that. Okay, so it's actually so interesting that in these 4 years, we started with that. People were only convinced about this kind of graph. It was really the totally standard event study, 0-1, because they said, then I understand what you're doing, distributed lag. Now, in the meantime, that is only in the appendix, and this is all that we have in the main paper. So the literature also, the understanding of that is also good. And I actually think that maybe, and we have lots of citations. Part of that is also that we convince the community of applied econometricians here that these two are the same and that they're allowed to do this kind of things. Okay. That's another type of motivation why this is an interesting paper, I think. It's just when you look at empirical papers in top journals, and we just included ARQJJP, which have more empirical papers, are all top 5. There was a huge increase in the last 10 years. And you can open any journal nowadays, you will find some graph. Good. So what is our focus formally? We're looking at panel data, and we're looking at two-way fixed effects estimates. So panel data estimates, you have fixed effects for individuals. So you actually absorb all these individual level heterogeneity that some people forever, or units for whatever reason, could have higher levels or lower levels. We are also, this is a paper about staggered treatment, which is in many applications. This is what people explore. Staggered means different units will have treatment at different points in time. That's different from the initial idea of standard event study, which was like there is one event, one group, all the other group had nothing, and then you just compare them. No, usually what we are exploiting in public labor economics is that it happens at different points in time. Very often we don't even have a group that never experienced it. So we're exploiting that the treatment was introduced for everybody, but not at the same time, and we want to exploit that. This will be very important when it comes to identification, because that actually produces, is in principle, in all generality, not identified, and we have to talk about what identifies this situation when you actually don't have a real control. Okay, then this is important, it's about homogeneous. So this is traditional econometrics. So in our equations, there will be a beta. Beta has no subscript, and we really mean this is a constant. Nowadays, people would say, oh, effects are never constant, they're always heterogeneous. All what we want to estimate are average treatment. And it's actually true that lots of people, when they see this graph, they also think this is the beauty of that. It's not just that we can look at pre-trends and the dynamic, the dynamics of the effect, but also that you can interpret this all as average treatment effects, because this is simple comparison of averages. That's true if you have treatment one point in time and the control group never treated, and then that's true. But if you have staggered treatment, this interpretation does not hold any. And that's a whole new literature, which is really important when it comes to important, which evolved at the same time as our. So our paper is a trivial contribution about an equivalence, and I think it's very helpful for applied research. People are doing right now, and these are papers published right now about how can you estimate average treatment effects of staggered treatments when you think that these effects are heterogeneous. That's much more complicated. That's a much more involved econometric literature. And first, with that literature, it's very important. What we typically do with two-way fixed effects cannot be interpreted as average treatment effects. So they make these exercises. That's always an average of something, but you can have weights which are even negative, which don't make any sense. So you don't know what this as a structural parameter should mean if there is heterogeneity. That's very different. But they also propose alternative estimates, which are always constructed out from making just comparisons of averages with some groups and so on. It's very involved. These estimates are now more and more implemented in RNS data. You can estimate them. If you're a PhD student, you should absolutely go for one of those estimates. But it's not my paper is about. I will have one page where I talk a little bit more about that. And I think when you understand what we're doing, it also helps you understanding exactly why it's a problem why the problem here arises, and when you can do this interpretation of average. But this is more important, but it's not what we're doing, which was difficult for us to get the paper then published, because it was always went to these people, oh, this is the new diff literature, and they would always tell us, yeah, but I mean, these reports like, yeah, this is actually not what's really interesting. You should actually look at heterogeneous effect, then you should look at staggered treatment, la 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 la. So yeah, that's the papers you've just read. So it's not what we want to do. So we had to find a journal that was willing to actually think there is also some value added from what we're doing, which we did. So it's now appearing in the Journal of Applied Econometrics. But it's very important that you know this is not the paper of this new difference in different literature.
Is it correct that we say that I think that's not dependent on INT, which means that for all of the indicators at all of the time points you have the same effects?
Which is like when we try to have a numerically model. That's what we do. We have a beta, and then we say, well, this is an assumption. It's a constant. It does not need to. In OLS, I mean, it's the same story. In OLS, when we write down an OLS model, we have this beta, and then in some situations, we are allowed to interpret this as average effects. If it's just a regression on a dummy variable, yes, it's an average treatment effect. But in all other situations, when you start having control variables and here time dummies and so on, this interpretation does not hold anymore. People still, whenever they see a graph like that, they actually think that's true. It even goes so far that Stata has now event studies implemented. They have implemented it exactly in the way we do it here, two-way fixed effects. And then do it either this or that way, accumulating it up, they're doing that, write standard errors and so on. This is all okay, but it's not average treatment effects. But the command would actually tell you event studies allow you to estimate every causal average treatment effects. This is how the command description starts, and that's really totally wrong. And it's in the description of the software. So that's really something that has, I think this literature is really super important. It did not get the budget. It's not what I'm saying. This paper is about these two things are very closely connected. It's important to understand. It's also about what's going on here when you stop looking at the effects. So that will be a large part of what I'm going to talk about. So that's how I focus. I will talk about standard event study design. These are the 0-1, and I'll just give you the formal methodology, how that looks like formally. And I will go to the distributed lag models and how these two are linked. And then once you understand that, I can do generalization and go beyond the 0-1 treatment and say, so what's going on if you have multiple treatments, if you have treatments of different magnitude. And then I hope to have enough time to look at the replication. So we're looking at the, which is really wonderful application, a paper in the Review of Economics and Statistics, which has very cool research design. And there's very strong effects when they look at different data and have no effects at all when they do the event study. And they make all the mistakes that we are actually showing here that you should not make. And if you rewrite, you get wonderful and convincing results. Okay, so what is the standard event study design? Formally, it's a simple regression where you have a linear model where you look at outcomes, different units at different points in time, and you regress them on event dummies, which have a T subscript, but also a lag, meaning this will tell you if the event was at the same T, that would be an L of 0. This is a dummy then, which is 1 at time of the event. So then there's another dummy variable, which is 1 year afterwards, 2 years afterwards, 3, 4, as long as you want to go. And then there is also the other direction at -1, at -2, at -3, and so on. And the corresponding betas, these are the plotted effects, which will tell you what's the effect after 1 year, at impact 1 year, 2 years, and so on, and before. So then we do have unit fixed effects, which take care of control for lots of possible confounding factors. And then we have time fixed effects. Of course, these are different points in time, and lots of things are different over time. So if it's about economic variables, this could be business cycles and so on. And then there is idiosyncratic temperature. So that's how you estimate the standard event study parameters. When heterogeneity comes here, we assume that this is really a constant. So now the first thing is what you need to do is a normalization. This is only identified up to one of those coefficients being normalized because of the unit fixed effects could always go up. I mean, you could always add 100 here and subtract it here, and it's the same model. So that's the first thing, you need a normalization. Typically, this is done at -1. So we say this is the period before the event, and then you look at what happens afterwards. Now, if you suspect that there is something like anticipation and you have reason to believe that, then this could be another time period right before where you think anticipation started. Good. So in practice, usually at -1, no big deal, but you've seen that Sebastian in the ER paper, they did not dare to, in all the situation, actually invoke this restriction at -1 because they thought distributed lag. I'm not sure if I'm allowed to do that. Good. Restricting the effect window. That is, so if you look at the graph here, we stopped here at some point and we stop here at some point. And in principle, you want to know what's going on until infinity plus and minus infinity. But of course, you cannot do that. You don't have the data for that. So what are you doing with the data points that you might observe up here and before here? So there are two things you can do. The first thing you can do is you can drop all observation outside the window. So you just say, I want to find it from -2 to +5. Everything which I observe outside of that, I would drop these data points. Maybe because there's only very thin information, only very few data points, and I drop them or you would include all the parameters you could where you have observations for that. So that's the first thing you could do. As you will see later on, this is actually a tricky thing if you don't have a control group which is never treated. So every unit is treated at some point, but at different points in time. This is actually something you cannot do. The model is not identified. We'll talk more about that. What we much more often do is what we call binning. We make assumptions outside of that. And the typical assumption is actually to assume, okay, the effect evolves over time. And at some point, it's there, it stays constant. It does not drop to zero, but it just stays constant. And that is what we call binning. So this is the assumption that we made here, which is say, well, from 6 years, it stays constant. And that's an assumption, that's a restriction. And the same here.
I mean, the major problem is that you know that you can't have this long observation period because then other treatments arise. So I mean, principally, you want to observe these guys for 30 periods or whatever.
Exactly. It depends a little bit on your data.
Right?
Yeah. I mean, the thing is, I mean, this is something you can practically, if you do have a large control group which is never treated, you could actually do that. And then you don't need to make, I mean, these are assumptions and restrictions are never nice. Now, it turns out that in practice, in most applications, this is a restriction that you need for identification. It's super important. And it's an experience that many people that work with this data have, that these two-way fixed effects sometimes seem to be very not robust. These estimates can jump around like crazy. And that's exactly because you have a non-identified model. And then they say, as soon as I start binning, everything behaves nicely. And that's not an accident. It's really because the binning is your identifying restrictions. I will talk more about that. It will become very important, but you need to do one of those things. In practice, this is what most people do, but they almost never talk about it because this is like, telling people that you're making assumptions, and it's not nice because you want to say this is non-parametric average treatment effects. So, okay, so binning. Binning means the most often made assumption means that you assume that the effect stays constant outside of some what we call an effect. So what we state in the paper is binning is very often the identifying restriction, but it needs to be stated explicitly. So it's a restriction, it's an assumption, and you have to really admit that you're doing that. Now, the problem is that people usually, when you read these papers, they just write down the equation. They don't talk about that they're doing binning. At most, they have a footnote, oh, we bin the endpoints. But it's never in their equations, and they never discuss if that in their situation is actually an assumption which makes sense. And it's a strong identifying assumption, in particular when it comes to assuming that on the right. I mean, this is really a statement. Could go down, it could go up again, and so on. So making this assumption here, and what you actually do by making an assumption that continues flat here, what you in practice do, this is like constituting the control group from here onwards. So you start up to here, you are treated, and then on the new level, you start being the control group for all these other observations, which might be treated here, 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 and here, right? And then it just says you, whatever goes on here is what goes on in the time traits and not in the effects. So this is an extremely helpful assumption, and it's good if it's true, but it's totally wrong if it's wrong. So what we say is just this: if you do this assumption, you have to admit it, and you formally write it down and make it very clear that you're doing that, and you also have to say. Now, we are not making a statement whether it's right or not. That really depends on the application. I think on the right, it's often very hard to make this assumption. On the left, it's much easier to say, well, in principle, I actually think there are no pre-trends anyway, so I just show it for a few periods, and all the other periods before, they will help me, they will be the control group. It's just by assumption, nothing could have happened before. But again, it's an assumption. It's much easier on the left. Okay, good. So formally, this restrictions means that outside of your effect window, and we define the effect window by L lower bar and L upper bar, the beta stays constant at the lower bar and at the upper bar. And if you just plug that into the standard equation here, you get a new explanatory variable, which we call a bin treatment adoption indicator, which is just the change. This is like the 0, 1 at the point in time within the effect window, and then at the endpoints, it's just summing that up to infinity, meaning this is a 1 if there was a treatment at that point in time or any point in time afterwards, and here any point in time before. So this is what people do when they do binning. This is a little bit tricky when you do that, when you form the explanatory variables, but it's absolutely doable. What most papers do instead of this definition, which comes immediately from the restrictions, they just say, okay, my event dummy is this. It's an indicator that tells me whether this is now a variable that gives me the time of the event, whether this event plus some lag or lead is the t where you observe the outcome. And then at the endpoints, you would just say, this is a 1 if that happens then or afterwards. So that's an equivalent definition. And this is the definition that you would find in most of these papers. Now, the problem with that definition is twofold. One, this is not at all generalized to multiple treatments and treatments that have a magnitude. And this definition one-to-one generalizes to it. So this is much nicer. The second one is you might not realize here what data you need to know about when treatments happened. Like when you have a panel, say from 2000 to 2020, and you observe outcomes, but also the events, you don't know whether there was a treatment in 1998 or whether there will be a treatment in 2030. But what you see from here, you actually need to know that. And that is, I think, the next slide is what is the information you really need to know? Yeah. So the information you really need to know to estimate that model is, if you think of the outcome variable being observed from t low part to t up part, you need to observe that an event happens when you have, let's put numbers into that. Let's say we want to know that 3 periods before the event up to 4 periods after the event. That's just as an example. You need to know what happened in -4 because the outcome here is the outcome 4 periods after the event. So you should know whether there was an event here, and that's on the other side. So you should know whether there was an event 3 periods. This is the outcome. You need to know whether, looking at pre-effects, whether there will be an event here. That was just 3 periods before. Now, it turns out you don't need to know this and that observation because it does not make a difference in your estimation. If there was an event here, yes, this is treated and everything is treated. But that just shifts up the whole observed time series by some effect, which is absorbed in the unit fixed effects. And the same happens here. You don't need to observe those. Now, that's very often when people actually estimate that, they actually think they need to observe, then they just plug in that -4 lag variable, and then observations, if you don't have the information here, are dropped. Now, if they would just add any information into there, whether a 0 or a 1, would actually not change the estimation, but the observation, the outcome is not dropped. And that's in practice then the reason when people actually compare the distributed lag with the event study, they would never get exactly the same results. And it comes from that. So here in the event study, as you've seen, I struggle a little bit to explain that because it's really a little bit tricky and complicated. In the distributed lag model, this is all automatically very simple. And we only realized that when we just never managed to get exactly the same results. And I said, but the sample's different, but why is that? Oh, but it doesn't use that information, but how comes that we need it in here? We don't need it in the distributed lag until we figured out, yeah, that's all because of the unit fixed effect. So you can just assume whatever happened here. But in your data, when you do the event study estimation, you just have to artificially put in information that you don't have. And you should say, let's put in a 0. I could put in a 5 or a 1 or whatever. It doesn't change anything, but it doesn't drop me close. So that's a little detail about what you need in terms of observing data. people using this definition did not care. They would always assume, like if I don't observe an event and there was no event, lots of units were considered as never treated, but we were not sure. And they became a nice control group, but which might not have been in a problem. So that's about data requirements. Okay. Now, the identification, I already said there needs to be a normalization, but there needs to be more than that. So imagine that you do have never treated units. So some units never had a treatment, and you're sure that they won't have a treatment in the future or had one in the past. Then this is a nice situation, and actually this control group will actually pin you down all these time fixed effects. And everything that deviates from them must be effects, and that's all good. So you can really estimate in a model from -infinity to +infinity wherever you have observations. You don't need any additional assumption. You also don't need to drop observations. You just include as many leads and lags as you have observed treated units. Okay. But very often we don't have that. And there's also a reason not to believe too much in. You could say, well, okay, then the situation is nicer if you have these never treated control. But now it starts to be a little bit a philosophical question. You don't never observe whether a unit will not be treated somewhere in the future, which is important for your treatments to get these effects. But then you can, but sometimes there are units that just cannot be treated. So that's super nice. So for example, you do a study on the effect of giving birth to a first child. Then you would say, okay, cannot have second treatment. And there are some units which can never give birth to a child, for example, men. So wonderful, I have a control group, can include. But then you would say, but men are maybe not the best control group for looking whatever happens to women because they're different. They cannot give birth to a child because they're different. And that could have an effect on everything else as well. So if there are units where you know they cannot be treated, they're not treatable, they're typically very bad control group because it means they're different. So in reality, you actually think that if you have a reason to believe that they cannot be treated, they're not a good control group. And very often we end up with a situation where we don't have these never treated units. So we can only exploit the treatment type.
I mean, in fact, this problem that you kind of exclude that some treatment happens in period t plus 20, right?
Exactly. I mean, for men, I can do that.
No, I'm just disregarding the men.
Yeah.
Okay. Just talking about women, right?
Yeah.
I mean, basically, you can't, of course, you can't exclude it that in period plus 20 something happens. But wouldn't it be sufficient to say, you know, in the kind of when 3 periods, that in the next 5 periods nothing happens, if you can guarantee that?
Yeah.
What is the real problem if you guarantee that?
If it's about the future, it's only about estimating the pretrends.
I mean,
you would say
that 5 periods pretrends is sufficient.
Yeah, right.
If that is, I mean.
But that's very similar to actually pinning on the left, which is not very problematic. If you don't know when something happened in the past because it's not in your data set, then you should really know whether there was not just treatment right before you start gathering data. And you need to have this information to be sure there was no treatment. And if it's not in your data, just assuming I don't observe it or it wasn't there, you cannot be sure. And again, depends on how far you want to go back in time and how long you want to estimate your effect. But the point is, if you're in a section where you don't have these never treated units, and I think that's the slide here, this model is not identified. And it's not identified because you could always add a linear trend to all your effects, meaning you could turn that whole effect dynamics and subtract the same linear trend from your time dummies, and you would get equivalent effect. And that leads on the unit fixed effect. If you don't have unit fixed effects, by the way, that's not true. But if you do have these unit fixed effects, you can do that. I mean, for any person, you turn these effects at a different point in time, but the unit fixed effects can shift up the level effects, and you get this equivalence. So this is not identified. If any unit was treated somewhere, so what can you do now? And it's exactly this spinning that gives you that information. If you say that at some point I think this effect stays constant. Whatever happened, there must be something that's going on in the time dance. This is easier done on the left. That's kind of saying, like, I don't care about too much about the future goal about treatment, and that cannot have an effect on what's going on now, which is very similar to saying, I think actually at some point this stays constant. But it's this binning that produces you the control group, which is like all the observation of those who are treated later on, but before, whatever happens to them, that gives you the floor, the estimated control group, the comparison. So this is why binning is so important, because in this situation, it gives you the identification. And it's what people experience in practice when they would say that their model is not robust. And that's really what many people experience. Like whenever they do the binning, things become very stable. Before they do that, whenever you change your sample slightly, the time period slightly, and then crazy things can go on. I mean, it's an effect can have like changed by a factor of 100 because it's a non-identified model, and this is just completely random what you get in terms of results, but just change your time. What also, how it's, I mean, also in practice, I mean, when I say it's not identified, why is your software going to estimate it? It's because it's dropping variables and it's dropping time downs, which is what people don't see that. So we just say, okay, then 2 years are just the same. And it's also, we don't realize that as applied econometricians, because we always know our time down is dropped because reference group, we've learned that, dummy variable trash, we always need. But then the software drops you 2, and you don't realize, oh, sample actually started early, it dropped me 2, and you don't see that. And very often nowadays, we even use commands that would not print us the time downs. So the software is just automatically dropping something that you don't realize to get the identification. It's definitely not what you want to identify, assuming that there is just between 2 arbitrary years, there is no change. But that's the reason. So whenever your sample changes then slightly, it's another variable which was dropped. So there's another identifying restrictions which you don't see, and that's why your parameters jump around. As soon as you do the binning, then it becomes very clear what you're doing, but it's an assumption. You need to state it, you need to define it. I think it's much easier to do it on the left than on the right. Okay. So that's one take-home message. Identification. Good. That's the whole story, which I just. The most extreme case of binning is actually difference in differences, fixed effects. If you were to say, oh, regression, I have a dummy variable for the treatment, it's 1. At the treatment and afterwards 0 before, that's exactly extreme binning, right? So you just allow for 1 jump and it's constant afterwards, it's constant before. We call it diff in diff and fixed effects, and we actually think there it actually needs less defense. When you talk about binning, people are very, I'm not sure, these are assumptions, I don't like them. If you do that, people say, well, that's just diff, that's okay, but maybe a little bit old. But it's nothing else but an extreme version of that. And that's the reason why when people do stagger treatment in fixed effects, diff and diff, they never run into this problem of non-identification. So in this traditional econometrics, this is a non-issue because you always get the identification from having after the event, this is going to be constant and gives you again the control group for whatever happens to be.
Still, you would need the parallel trends, so it gets a little more complicated. And not so simple, right? It's
also, if you would actually say that's true. I mean, if you would say, we don't want that, it's absolutely okay to just do this. Then this is the assumption, here is a 0 and it stays 0 forever. This is binning. It's an assumption which is say nothing happened before. Which, as I said, on the left, that's not very difficult to defend. You would just say, oh, I think there's no anticipation. I assume parallel trends before. And that's my identifying assumption. That's it. As I said, here it's easier to defend.
And it's good that you can say that. I mean, the question is how convincing that is at the end of the day, right?
Yeah.
And I would say probably typically no referee would accept that. Right?
Yeah, nowadays people would actually say, but I want to see that before. As soon as you show that, you estimate it at the same time. Still, at some point you have to say, this is finished. And now it's constant because I need those observations to give me the control. It's just a question, where does that start? But at some points you need them. It's also, you don't show them. I mean, if I would plot them here, and actually then I would really admit this is part of my estimation strategies to say that these are good. Okay. So I have to speed up a little bit. Estimation. So now this can be estimated standard. This is a OLS regression, panel data, two-way fixed effects, whether you do it with or within transformation or whatever. It is, well, you can do it in levels or you can do it in first differences. Now in the event study, the first differences looks quite strange, and I think I do have the, sign matrix here. So in levels, this is the big treatment variable, which is just like these events. This is at -2, -1 is dropped because it's the reference group. This is at 0, 1. And then at the endpoints, this is like this accumulating it up. This is not just done at the point, but it's also before and afterwards. So that is what most people would estimate here. If you do it in first differences, you get these very strange design matrix, but it's totally correct. You will see when you do distributed lag, this is what you're estimating in there. This looks totally natural in first differences, but I will show you that. Good. So this is a slide about average treatment effects. As I said, this whole new difference in different literature has been that you cannot interpret these beta and two-way fixed effects models with staggered treatment as average treatment effects on treated. You can do that if you have a never treated control group and they're all treated at the same period in time. Then these are simple comparisons of averages. And wherever you stop, this is okay. Whatever is left is the average over all the remaining lags and so on. It's an average not just over different people, but also over different time horizons. But it's average treatment effects on the treatment you have. It's a little bit tricky to define what treated are, but it's an average treatment effect. That's all good. As soon as you have staggered treatment, this is all gone. And that is what this whole new literature has shown. One simple solution to that, and I think that's the most intuitive of those estimates, is Sun and Abraham. I like that most. They would just say, well, for any treatment cohort, like this is a group of units which have been treated at the same point in time. And if you do have never treated units, which I think it's hard to defend, but if you have them, you can just estimate these event studies for each treatment cohort. And then you get different coefficients, and then you just take weighted averages, weighted by the size of these different groups. That's basically what Sun and Abraham is, super intuitive. And these can be interpreted as average treatment effects on the treatment. And for the individual group, they call it the cohort-specific average treatment. It's intuitive. It's also very intuitive to understand why it works. But it totally relies on having this never treated control group, which I find in many cases is problematic. Good. So now, contribution of that paper, the relation to distributed lag functions. And now that's the main result here formally. This is the event study that I just showed you, which already had the binned treatment indicators here. So we have let's put numbers on it. So this is a model where we want to find the effects from -3 to +4, -1 is the normalization. And at the endpoints, we make the assumption that the effect stays constant. So we have these binned endpoints. That's the equation. Now what we can, super easy to show, this is totally equivalent to a model, a distributed lag model, where you have outcome in levels. You're regressing on the treatment, but not the treatment indicator at the point in time, but treatment status. So T here is a variable which is 0, 0, 0, 0, jumps up to 1 and the treatment stays at 1. So that's the level variable for are you not treated, or are you treated, no, and are you treated. So that's a regression of levels, but including leads and lags, right? So these are coefficients gammas here that gives you, okay, so you have this treatment in levels, but a period before, 2 periods before, and so on. Now, these two things are absolutely equivalent if you have here binned endpoints and you start at -3 to +4, the distributed lag model that starts at -2, not at -3, has no normalization, so there's no gamma drop here. -1 is included, goes up to 4 as well. This is absolutely identical. And the assumption here that the effect stays constant after the endpoint and before the endpoint is the same as assuming here that these gammas are 0. Meaning, if people wrote down distributed lag models, they would just say, well, we have to stop at some point. It's okay. We allow for the effect to take some time, but then it's 0. So,
excuse me, this gamma is an index J? Or?
That's a J. This is again, the gamma is like the index that relates to the event time here, right?
Okay.
So gamma 1. J1, J2, J3, J4, 5. So this that's the J. The J is the dynamics of the effect. Exactly.
But in the formula there's no summing up over J.
That is not, yeah, it comes. So these two come. These two specifications are totally equivalent. It's not the same coefficient. And what's the relation in the coefficients? These gammas are not the effects after 3-4 periods. It's how these effects changes. Right. So that's what you have here. So the betas are these points here, and you estimate them directly. The gammas are the changes here in these betas. And if you want the betas, you can just accumulate up the gammas. That's the relation between the two. And when I say you do not drop the -1 in the distributed lag model, you do estimate all these gammas, but then you start accumulating up here and plus and here minus, right? So you accumulate up and you accumulate down here. This is how you get all these points. So the normalization actually only kicks in when you want to get the betas from the gammas. But these two things are formally totally equivalent. The interesting bit, or one of the interesting bits is, I think, the binning assumption relates to having leads and lags that stop at some point, 0 restrictions on the gammas, which in the old literature that had just lags, which you say, yes, at some point you just include another lag and then you stop. It's a 0 restrictions and nobody felt really obliged to defend that too much. Well, when we talk about binning and we say, okay, the cumulative effect stays constant if the incremental effect is 0, that's the same expression, but it sounds like, ooh, but this is really strong, you need to defend.
But that's the rhetoric point, right?
Hmm?
I mean, that's a rhetoric point.
Exactly.
Just to say that you don't need to argue why you stop the lags and leads, right?
Yeah, but I mean, this is what you get from referees. If you estimate the distributed lag model, and you would just, nobody will ask you why you're making this assumption. But when you do binning in event studies, everybody will say, like, ooh, this is really, I don't know whether I believe that. Now, the point of this paper is to say, this is the same. This is a reparametrization.
So they should argue about the number of lags.
Yes.
More.
Yeah.
This is the answer, right?
The one is not better than the other, it's the same. And it's not just about the same or intuitively the same, it's formally, it's dead.
Identical.
It's identical, it's equivalent, it's the same. It's isomorphic. So it's totally, and I think that helps the discussion because you can really, and sometimes it's helpful to think in distributed lag model, whether it makes sense, and sometimes it's helpful. The distributed lag model, then, as you will see, is also much easier to think about generalization. In the event study, this is really like, I don't know, it could be intuitively make sense or not. In the distributed lag model, that's just a linear regression, and then you allow these things to be continuous rather than a dummy variable, and that's all. So this is all taken for granted there. What is there else? And this equivalence also holds in first differences. And now in first differences, when I said this is a weird regression here, which has these -1, 1, this weird design matrix. In distributed lag, this even makes more sense because what you're saying here, this is a regression where you say the changes today or in point T can be a result of changes in the treatment status at this point in time T or before. And so you say here is a change in the event. So there's an event, and this has an effect on the change today, on the change next day, and so on. So this is a regression that is, for me, the most intuitive one. And it's also here, it's not very weird to assume, putting numbers, that it does not go on forever, and it's just zeros outside. Which is say, this is my effect window outside 0. But implicitly or explicitly, you're doing binning here, because that's the equivalent. I think that's the main formal result. It's an identity, it's a 3-liner formally, but it's something that to us was not obvious, and I think to most referees and editors was also not obvious that these two things are really easy. So that's the main message. Okay. Normalization only comes when you start accumulating up. This is again ADR. The editors and the authors did not dare to put the 0 here. This is distributed lag. I don't know if I'm allowed, and we better don't do it. So, exactly. So, but they should have done. Good. Same about identification. It's the zeros in the distributed lag that give you the identification, and there you can really see how these form the control group. Because they're not treated outside. That's just the visual way of showing this accumulating. Okay. Estimation of the distributed lag model again. These are simple regressions, fixed effects per units, and time dummies. They have standard properties. So this is usually, we think of that in microeconometrics. So we have large N, and we look at the asymptotics. T is fixed, N goes to infinity, and then these estimators are consistent and asymptotically normal and have all these nice properties. But effects are assumed to be constant, of course, otherwise this so and strict exogeneity and everything. Yes, good. That's the design matrix here in the distributed lag, and what we can see, I mean, this is the most easiest kind of specification. It's distributed lag model in first differences, where you can see it's just a regression of changes on all these treatment dummies with lags and no normalization, and just stops at some point, and then you get your effects, which are the gammas, and you can accumulate them and do the same thing. I mean, using the correcting of doing the standard errors from. This is linear transformation. It's very easy to do. Good. Practical implication. Which one should you estimate? Doesn't matter. It's the same model. So I actually think the distributed lag model is better because it's much easier to actually put it to the data. So the construction of these bin treatment dummies is kind of delicate. You can make lots of mistakes. Absolutely nothing. Also, you don't have to worry about how many data points do I really need? Oh, at the endpoints, I don't need to know whether there was an event. Here, it's all very simple. It's just like you take the leads and lags, no new creation of variables. That's all gone. Simple regression, and it's all perfectly right. So we think it's much less error prone. So the coding is much simpler. It becomes a little bit more difficult because you get the gammas, and you're interested in betas. So you have to do these. Yeah, what's the standard errors for adding up parameters? But the software is going to do that. It's also needs a little bit of coding when you want to produce the graphs, but it's super. With the standard errors, it's easy. Okay.
Sorry, I have a small question.
Yes.
Isn't the distributed lag estimator more efficient since more observations enter into the estimation? Isn't this the case, or am I wrong?
You're wrong, but it's a good question.
Yeah.
And it's a second one. Oh, yes, it's really identical. Yes, they're really identical. And therefore, the question is not which one is better, which one is more efficient. They are exactly the same. Now, in practice, why do people almost never find the same thing? Because they drop observation they should not have dropped. And if they do the coding right, even in the event study model, those are not dropped because they should not be dropped, because you don't need to know at the endpoints whether there was a treatment or not. Once you do that correctly, you get the same number, and then the question, which one is more efficient or better, is obsolete. But it's a good one, and it took us really months to figure that out, that it's not just theoretically, but also practically the same. Okay, but then there's a question, fixed effects versus difference, but that's usually in panel data. Yeah, it's not the same. They should all both have the same properties in the sense that they're consistent. They should converge with the same parameter, but in a small sample, they're different. Now, depending on the time series structure in your error term, fixed effects of versus difference is more efficient. I think it generally is. If you have a white noise, fixed effects is better. If you have a random walk, versus difference is better. And in between it's somewhere. But in principle, they should be pretty close. I will show you in practice. This is also not true, but I show you that with yes, which is interesting, which helped us a lot to understand why are fixed effects and first difference is not the same in practice, and they differ a lot when I do that in practice. And then there's always the discussion in textbook, it's about efficiency, but this is a main result, it's about the dynamics. And if you get the dynamics right, they're actually practically the same. And I will show you that in the example. Good. Generalized event study before going to the example. Now, when you've written down the distributed lag version, what we have here was in the event study or the event study equivalent, this is the treatment status variable, which is a variable which is 0, 0, 0, 0, jumps up to 1 and stays 1 forever, because a treatment can only happen. Now you can say, I don't need to interpret this as such a variable. This could be any variable. It could just be a continuous variable. And then what I have here is a linear regression model. So if there's something big happening here, it should have big outcomes. In particular, if I don't have the difference equation here, but in first difference, it is even clearer. So if I have a big first difference, you have a big effect. So there's nothing that prevents me from interpreting this equation generally as this being a continuous variable. So I can include multiple treatments. That would be 0, 0, 0, goes up to 1, 1, 1, then goes up to 2, 2, 2, goes up to 3, 3, 3. And I estimate this equation. I don't know what to do when I use the event study equivalent, other than if I translate that into my event study specification, and I use this definition of the bin treatment variable. Then this still is equivalent. And this will be a very strange bin treatment variable, but it produces exactly the same. So in this generalization, it's much simpler to think of the distributed lag model and convincing yourself it's the right thing. But there is always event study type levels on first differences specification that is doing exactly the same. And in the end, you get the gammas and you just accumulate them up. And you can plot an event study graph, although behind that is a simple linear regression with lags and leads. Now, you do get this only with assumptions, and that's the linearity assumption. So behind that is, if it's just multiple treatments, the second treatment has the same effect as the first treatment. If you don't believe that, well, you can also include the second treatment as another explanatory variable and having a different effect and so on. And if this is a continuous variable, it's also the assumption, yeah, if double the effect, double the treatment means double the effect. Changing the sign, so if you increase a tax rate by 1%, this has the same effect as decreasing it by 1%, but with a reverse sign. That's an assumption. But from that assumption, you get a lot of power to identify your effects. But of course, it's an assumption, so you have to defend it. You get as a plus, not this arbitrary control group of very weird, somehow treated groups, but you buy it with the linearity. Of course, if you don't believe it's really linear, you can also start including polynomials. You can also add control groups, control variables as you like. That's a linear regression. So put in axes with leads and lags and whatever. You can do whatever. This is traditional econometrics. All you do is accumulating up these effects to produce the graph people want to see. Good. So that's the generalization. And people struggled a lot with what am I doing if I have multiple treatments? What am I doing if I have treatments that can be applied and then reversed? So what if it goes 0, 0, 1, 1, 1, go back to 0. And this just tells you, well, if you're willing to make this assumption, then this is how you should do that. And it also means if you do the bin treatment dummies, that's the equation you need to use. And this version which is usually used in paper with the treatment timing does not happen. That doesn't generalize. Yes.
So something like if you have multiple treatments, essentially you are potentially treatments that are outside your observation, then you always have some kind of potentially missing missing variable population because you cannot assume anything away. So if a treatment potentially that 20 years ago still has an effect, you don't observe the reason, but then it's a problem that you can.
Well, that's the binning part, right? I mean, we still have the binning part where we would say, if you would say this goes from -3 to +5, then you do not need to know whether there was an event or 2 or 3 events 10 years ago, because you would say after 3 years, it still had an effect, but the effect was constant. And meaning if it's constant, then I don't need to know it because it only shifts the level that goes into the unit system. So if you don't believe that, that's the binning on right, then yes, if that could go on forever, yes, yeah, exactly. And you need to observe what was going on before, yes, okay. So that's the generalization, and that's just a way of writing that. I mean, just to put categories, you can do single treatments, multiple treatments, single treatments with different magnitudes, and then the most generalized multiple treatments, different intensity, meaning a linear regression on a continuous variable. What's also nice to show here is the single treatment with varying intensity is a regression of levels on changes, which is what the AR editors thought is very weird. And it's exactly what you would do. And it's exactly scaling your treatment dummy with the size, with the magnitude of the treatment. And there are papers out there which did that, but they usually did not write that down formally because they thought, I'm not sure it does not look nice and important. So we just put it in a footnote or in a note of the graph. And you actually see that. I mean, they would write it down like it's a 0-1 event study. They would say, this is total event study. And then there is this little sentence below the graph. Oh, and by the way, we scaled the treatment by the size of the treatment without writing that down formally. And so this paper helps you. Yes, you can do that. You're allowed to do that. You're just doing a linear regression, the linearity assumption, and you can write it down as a distributor. So that's all about the basic story. And now let's actually go back and review that again with one example. And that's a study by Baker and Fratkin in the Review of Economics and Statistics. And it's actually a cool paper, 2017 published. What they would look is potential benefit duration in the US differs across states. So how long you get unemployment benefits. And it changed over time. So some states increased that and decreased that. And what they wanted to show is, does this have an effect on job search intensity? So you could actually think if your unemployment benefit duration goes up, you're less likely to look for a job. Now you need a variable to find that. And this was what's cool about the paper. They look at Google job search indices index. So Google at the time started to look at search items, and it would look in different states where people typed new job here, new job in Kentucky, and so on, and they would report that. And if you look at the time series, you could say whether there was more job searches going up and down. Of course, the internet was exploding at the same time, so you need time dummies. So two methods. So that all sounds good. They estimated that model, and they did fixed effects, just looking at large increases of potential benefit duration, meaning more than 13 weeks. That's quite arbitrary. And they did diff in diff, just including the treatment dummy when there was such an event. And they got very large effects, meaning if your potential benefit duration went up by 13 weeks, job searches went down by 2.1%, which is a big effect. Then they thought, yeah, that could take time and we want to show that. And now everybody starts doing event studies, so we want an event study. And that was the result they got. That's the published event study in their paper, which was like never significant. somewhere going down even, not convincing. And then we were looking at that and said, how can they do that without the normalization? Why not? I mean, already if you move that down to a 0 here would help a lot. And what's going on here? Are they doing binning or not? The paper would not explain you anything. But they made the conclusion, in conclusion, our event study methodology fails to find evidence of large job search responses, changes in potential benefit duration. It's too bad, and shit happens. Diff and diff is good, and this is somehow inconclusive, and I don't know. So what did they do? How can they do without the normalization? They have to do that. It's not identified. And then this is that treatment. All these states were more sooner or later, they had such a reform. How can they do that? Well, they do both. They do a normalization and they do binning. How did they do that? The normalization is, they dropped all these variable, meaning they have a 0 here. And they have a 0 here, which is very weird. So they assume that outside of the effect window, where they don't show the result, it's a 0, and not here. So of course, because there needed to be an effect, there is an effect overall, but it cannot start at 0 and then jump up. It had to already be high up here. So it's very, very, very ugly. What about the binning? Well, they also think the 0 stays forever. So they're doing the binning on both sides and don't talk about that. They don't know that they're doing that, and they have the 0s. So first thing we did is estimate that doing proper normalization and allowing for the same binning, the same effect window, and doing the binning here. And that's what we get then. Okay, -1, that's the reference period. There is an effect. It already goes down, not significant, but after 4 periods, and these are 4 months, it's already a very strong effect and very much in line with what they did different. That's nice. Good.
We just the normalization bringing -0 to 1, to 0 basically.
Now we're basically just moving that whole thing up to here.
That's kind of a very simple point.
That's a very simple point. But it's published in the Review of Economics and Statistics, and no editor, no referee has actually realized this is a completely misspecified question. And then the binning. They have staggered treatment, they also need the binning for that. But why stop here? And actually, there's already one indication that says, oh, it goes up, and then there is a big jump here. Maybe the effect is not end up here. That's the next thing we want you to do. But before that is actually, yeah, but why just doing that 13 weeks and all the rest, these small increases, decreases, blah, blah, blah. Let's do the generalization and include that. If it's 13 weeks, if it's 26, it's double the effect. We just do that. Distributed lag, including all the minuses and size and so on. And what you get then is a much, much stronger. Because now we have much more identifying variation. Not only do we use that there was something big going on at some point in time, but we also use all the small changes, the big changes. The big changes should have bigger effects. This is all overlapping. So if there is a small change after a big change, this should have then, yeah, this is all nicely included and all the reference groups are correctly dealt with if you believe in the linearity assumption. But what you get is a much, much stronger result, even much more confirming the diff result. We still have a bigger effect here, thinking the effect is not over. There is a question.
Sorry, just making more on the impact evaluation interest. Is binning such an issue if you really just want to interpret it for the oscillation period? You don't want to extrapolate on it.
As I say, the binning is absolutely crucial because it's your identifying tool if you don't have a non-treated control group. If you have a non-treated control group, binning is not crucial. But in many applications, people do not have that. Or it's a very small one, it's not a convincing one, because you think maybe they're different than other control group, maybe they're only very few, and they're super important for your identification. And then saying binning, relying on what was going on before the treatment, is much more convincing as a control group than relying on very special, strange units. Right. But this is really, in your application, you have to argue, what is my control group? This is like going back to basic research. If you want to find the effect of something, you need a control group. This is what medicine has learned, right? I mean, if you need a treated group, you need a control group. That was how empirical research started. And in econometrics, things are a little bit complicated, and we've lost thinking about, where is my control? But here with the binning, you define the control. Or if you have never treated units, then these are people, but you need to know how big are they conditional. Talking about the control group is as important than talking about your treated group. So here it comes a lot from. Now let's actually see whether it comes from the binning here. It does not come from the binning. So I think it's not convincing, and this is why we started to increase this kind of lag. So this is 4 lags. And you see a big jump here. That's just repeating the graph that we showed before without the confidence intervals. Now we start to increase the number of lags. And what you see, of course, my sample size shrinks because now I have more lags. So the sample size is always different. I continue that. It goes on up to about 1.5 years. And then you see it starts flattening out. So that seems to be a much better modeling of these dynamic effects. And what you also see is this effect gets really much larger than what you would have estimated here. And you also see at the end, there is not this kind of kink at the very end. But now you could say, but this is a completely different sample. So we can go back to the initial sample here. And what you see is now the sample doesn't make the slightest difference. I mean, this is not a small sample, but only 4 lags. It's the same. So this seems to be the long-term effect, very nicely estimated. Now the last thing, this is done in levels. You could also do that in first differences. And then what you see in first differences, you never have this kink at the very end. Because you cannot formally interpret this as an average treatment effect, but it's still in level, it picks up what's going on in the future. Formally, it's not consistent or unbiased estimate for all these time horizons, but in practice, it captures that in levels, but not in first differences. And that's really the difference between first difference and level estimation. A first difference takes timing very, very strict. Only what happens exactly at that point in time, or the lags that you're willing to include, is captured in your effect. In the levels, everything here and in the future will be picked up. And this is the reason why when we don't having lags, when we do estimation using fixed effects, we very often have large effects. When we do it in first difference, we have very small. And the reason is the model is misspecified in terms of the timing. There was a big effect, but it was not happening at point 0, right? And then you get exactly these differences. Big effect in levels, no effect, or very small effects in first. Now, this is misspecified because looking at the data-driven, we would say it's 1.5 years, and here we have only 4 months. If you do that for 1.5 years, then you would actually not see this kink in either of them. They're not the same estimates, but within confidence interval, they're totally same. Both are consistent, good estimates, but that seems to be the right time horizon. Now, when writing the paper, people told us, yeah, but now it would be nice to actually have a kind of a formal way of finding this lag lengths. And you should provide us a test when we should stop, like when it's not significantly incremental anymore here. But we did not want to do that because in terms of testing, as a formal test, this is very tricky. Because this is all kind of tests based on task-dependent decisions before. And as you know, this is, and I think this is in Vienna where people, what's his name? Pötscher. Exactly. So, I mean, if I do 18 tests in a row here and then I decide now it's not the properties of that test after 18 lags, we have no clue about what these properties are. So we cannot provide a formal test.
So, but in time series, you have all this information criteria that you
Yeah, that could be an alternative. Yes. But in terms of the formal test, we did not want to go into that. But as a practitioner, I actually think this is usually quite, I mean, in this example, I think it's quite to see this is the graph they should have given in the paper. And of course, this is super convincing evidence. And the first results we present in the paper, which is definitive, highly significant, that's right, but it's a very imprecise result. And doing that, the right lag lengths, the right normalization, allowing for the right binning, and then including the quantitative information leads to a much more precise, nice, convincing result. So, and if they had read our paper back then, this is the result they would have used. Good, and that's it. And I think the conclusions with all the things that I already told you. The main formal result is distributed lag with a limited effect window is identical to an event study specification with binned endpoints on both sides. It doesn't matter which one you want to estimate in terms of implementation. The distributed lag is more convincing in my view, and also you can easily generalize that to multiple treatments and to using the intensity of the treatment of quantitative information. But we cannot offer anything on if you don't believe that these effects are homogeneous, then two-way fixed effects such as linear regressions do not reveal average effects. And you have to go to one of those new estimates. So although when it comes to multiple treatments and treatment intensity, there are not yet general solutions for that. For the basic story, we have solutions, but not for these generalizations.